So, this is lecture 2 of electromagnetic waves. In last lecture, we essentially discussed the formulation of the Maxwell equation. About the Maxwell equation, there are 4 Maxwell equations, and from the Maxwell equation we obtain various conditions, and using that condition we essentially draw how we understand how electromagnetic waves essentially propagates in vacuum. Okay. So, in this class we will discuss about the we will discuss about the integral form of the Maxwell equation. In last class we basically discussed the differential form of those equation, but today's class we will discuss about integral forms. Not discuss, actually we will just understand the integral forms, and for that first we will recap our previous class, and then we will start with the displacement current. Okay, and for displacement current first we will study the Ampere Circuital Law. Okay. So, what we discussed last class. Okay. So, first we learn about our Maxwell equation. First we discuss about electric field and magnetic field, right? Essentially, electric field is denoted by E vector and magnetic field is denoted by B vector. Okay. And then we discuss about our Maxwell's equations. Right. Basically, the differential forms. Okay. After Maxwell equations, we obtain some condition regarding our wave vector, electric field and magnetic field, that all are the perpendicular to each other. Wave vector, electric field and magnetic field all are the perpendicular to each other, and from there, from this condition we essentially draw our electromagnetic wave like this, right? How it propagates. Okay. So, here this is the direction of k vector, B vector and E vector. So, okay, let me just recolor it. Okay. So, this is our electromagnetic wave. So, we discuss about these things in last class. Today's class we will start with displacement current. Okay. So, our first topic is displacement current. But to understand displacement current, we have to learn about Ampere Circuital Law. So, for displacement current, I will first discuss about Ampere's Ampere's Circuital Law. Ampere Circuital Law basically is the chapter of electromagnetism, but in this context we need to understand this law. That is why I am going to discuss this Ampere Circuital Law. So, what is first we have to understand what is line integral or the path integral. So, let me start with line integral. What is the line integral? Let us say this is a very small segment, dl segment, and a vector is present. This is a vector, any random vector it may be. Now, this segment is dl segment. dl is also vector, so this vector will act like this through the tangent. Now, and the magnitude of the dl vector is guided by the length of this segment, dl segment. Okay, and this angle between this a vector and the dl vector is theta. Then what will be the dot product? A dot dl, it will be A dl cos theta. Okay. So, this is for this a very small section for dl section. Now, if we consider a path or a line like this from P to Q. Okay. So, we can divide this PQ segment in infinite number of small dl section. So, let us say this is a dl section, then this unit vector will act like this, and any vector A vector, let us say this is working like, and this is theta. Okay. Now, A vector, A may be any random vector, that may be force, that may be electric field, maybe magnetic field, any vector quantity is present, is operating through that line, through that path. Okay. So, now the direction of A vector is also not specific, that is guided by that angle theta. Okay. So, now we can say that for this small dl section we can again write this formula, but for the total length from P to Q, for total path of the line, we can write that limit. What will be the line integral? What will be the line integral? The line integral will be limit n tends to infinite sum over I is equal to 1 to when, I will discuss what do I mean by this L I. Okay. Why? This part is this one. Okay. For that small dl part, now we can break our total length from P to Q, that length in n parts. So, the summation appears from I equals to 1 to when. Now, if this n is tends to infinite, that means essentially we have break our total path in infinite number of small dl length. So, that is why this will be our line, total line integral. So, what we can write? As n tends to infinity, we can replace our summation by integration, we know that very well. So, integration from P to Q, it will be A, and the del will be replaced by D, dl. So, it will be V to Q A dl cos theta. So, this is our line integral or the path integral. Okay. So, this is, let me write, this is our line or path integral of vector A may be any vector, importantly along the path PQ. Okay. Now, theta may be changed as I said, because here the theta is actually guided the direction of the vector A. Now, the direction of the A vector is not specified, so theta is also not specified, theta is also varying. Okay. Now, this is the open path. Let us say if we close the path, if we attach the two ends P and Q, then it will be a closed path. What will be the changes if it is closed path? Let us say we are discussing now for closed path. Any closed path, this is a closed path. So, for closed path, take again any very small section, this is a small section, this is the line element, this is, let us say this is A, and line element will act like this dl, and again this is the theta. Line element, the line dl vector always work along the tangent. Okay. So, again similarly we can write a overall part is the same, just line integral will be, now this is a closed loop, so it will be the path is closed path, because the loop is closed. In previous case the total path is open path from P to Q, that is why we put P to Q. Now, we have to put from P to P. Okay. So, that is why we use the closed integral. So, it will be close A dot dl. So just same, just it will be just closed integration. So it will be A dl cos theta for the closed loop, this one, and for open this. So this is also the same thing. This is also line or path integral, but for a closed path, and this is for the open path. Okay. So now we will see some example, just like what will be the example. Very important example is very that is that line integral or path integral of force vector F is essentially the work done. Okay, how? What will be the path integral for force? That will be, it may be closed, it may be open, we do not know. For very small segment we can write that, first we have to write for the small segment, dl segment. So that will be f dot dl as we write before. So it will be f dl cos theta, and we know that f dl is the dw. Mind it, as it is dot product of two vectors, it will be essentially a scalar. So f is a vector, l is a vector, but w, the work done, is a scalar quantity. Okay. This is displacement force. Okay, right. Now this is for very small segment, dl segment. For the path pq path, for pq path, it will be integration dw is equal to integration from p to q, obviously from p to q, it will be f. Now dl, not dl, it will be not del, instead of delta l, it will be dl cos theta. Okay, and for closed path, let me write closed path or loop, it is actually the w f dl cos theta, or we can write it f cos theta dl, does not matter, the same thing. Okay. So this is the work done. Work done is actually the line integral of the force. So this is also similarly the line integral of different vectors are very much important, that has some physical significance as well. As here you can see that the line integral of force is actually work done, that is another quantity, important quantity. But again, for other vectors like electric field, magnetic field, there is also some line or the path integral that has also very significant impact. Okay. Now if this force is conservative force, then we can actually write it like this, for conservative force only, because in case of conservative force, the force is always constant for all point. If we consider any path or any loop, the force each point is constant, so we can out that part from the integration as it is constant. Okay. So here, for example, the line integral of the electrostatic field, the E, electric field, around a closed path is 0, because electrostatic field is a conservation force field. Okay. So we can say like this. Here one more thing, yes, for conservative force we can write, okay, let me write it clearly. For conservative force, what I said, that f is constant. So as f is constant, so we can write that the line integral or the path integral is equals to f cos theta dl. Okay. So it will be actually 0 in if f is a conservative field, conservative force. Now in case of conservative field, for electrostatic field line integral will be, this is line integral for a closed path, E cos theta dl, again it will be 0 for conservative electric field as well. Okay, so this is due to the conservation of the field. Now what is the Ampere, what is the statement of Ampere's circuital law? Okay, so let me write it clearly. The line or the path, anyone we can mention, integral of the magnetic field vector, actually magnetic field is a vector quantity, so which is B, along a closed path, mind it, closed path in any magnetic field is equal to the product of the net current, which is I, enclosed, very importantly, enclosed by the closed path and the permeability of the vacuum, okay, which is mu naught. So this is the Ampere circuital law, which says that if a line or path integral of magnetic field vector B along a closed path is equal to the product of the mu naught, that means the permeability of vacuum, and the I means the total electrical current, net current enclosed by that, importantly this is very important, enclosed by the closed path. Okay, so what will be expression, mathematical expression? First is the line or the path integral of magnetic field, it will be BDL. We can write it like B cos theta dl, does not matter, it's same thing. So it is BDL. Now according to Ampere circuital law, this BDL is equals to mu naught I. Okay, where the mu naught is the permeability of the vacuum and I is the electric current enclosed by the loop. Okay, so this is our Ampere circuital law, where this part is essentially line or path integral of magnetic field, and mu naught is the permeability of the vacuum, and I is our electric current, total electric current enclosed by that loop. Okay, so we have to now see some explanation. Consider this is a electrical wire I. I is the current flowing through this electrical wire, and this we are considering any loop around this wire. So then what will be our Ampere's law, that B dot dl equals to mu naught I. Now let us say if we consider any loop which is not enclosed that wire, then essentially that will be 0. This loop, let us say x1, this loop x2, then for x1 it is mu dot I, for x2 it is 0. So, this is the significance of the Ampere circuital law. Thank you.